When an object is heated, the molecules begin to move faster and spread apart. This leads to an increased amplitude of oscillation and distance between molecules. Thermal expansion will apply to every dimension of the object, but let's first consider it applying to one dimension, and this is called linear expansion. So if we consider an object that has an initial length of Li, after heat is added, it expands to final length Lf. Then the new length of the object is given by this relationship here, Lf equals Li plus Li alpha delta T. Alpha is a constant that's specific to the material, and it's called the coefficient of linear expansion. It's in units of per degree Celsius, or degrees Celsius to the -1, so degrees Celsius inverse. Then we have delta T, which should be in units of degrees Celsius here. The length units can be anything as long as they're the same on both sides. So often it's written either like this, Lf equals Li times 1 plus alpha delta T, or we're interested in a change in length with temperature opposed to just the final length, so we can write delta L equals alpha Li delta T. So as heat is added, the substance will expand and the length increases. If heat is removed or the substance is cooled, then its length will decrease and we'll have a negative change in length here. Okay, let's do an example. Example 5, the height of Seattle's Space Needle, mainly made out of steel, is 180 meters on a 0 degrees Celsius winter day. How much taller is it on a hot summer day when the temperature is 30 degrees? All right, so we'll need to find the coefficient for steel. It's 12 times 10 to the -6 per degree Celsius, which you can look up in a chart. And then we want to find the change in length. So delta L equals alpha Li delta T. You can also put L naught here like we've been doing for initial and use no subscript on the final. That works too. Okay, so alpha is 12 times 10 to the -6 per degree Celsius. The initial length is 180 meters and the temperature increase is 30 degrees Celsius. So this would be a change in length of 0.0648 meters, so about 6.48 centimeters, which is significant, but remember this is 180 meters and it's quite a big temperature increase. Example 6, steel train rails are laid in 12-meter long segments placed end to end. The rails are laid on a winter day when the temperature is -2. How much space must be left between adjacent rails if they are just to touch on a summer day when their temperature is 33 degrees? Okay, so we'll need to look up the coefficient for steel. It's 11 times 10 to the -6 per degree Celsius. And you can see that the coefficients generally for linear expansion are on the order of -10 to the -6 for solids, so that's why we're not seeing huge changes with normal variations in temperature. But okay, let's find delta L. It's alpha Li delta T, so we'll have the change in length, so we know how much space to leave. 11 times 10 to the -6 per degree Celsius times 12 meters, and then 35 degrees since it's going from -2 up to 33 degrees Celsius. And this gives 0.00462 meters, or 4.62 times 10 to the -3 meters. And that gap has to be left somehow. So whether this would mean leaving this at the end of each rail or doing half at each end of the rail, that's the room that needs to be left for the expansion. The concept of linear expansion can be applied to each dimension of an object, and when we look at it overall, we can consider its volume expansion. So these formulas look very similar to what we saw for linear expansion. We have the final volume Vf equals the initial volume Vi, 1 plus beta delta T, or the change in volume equals beta Vi delta T. So beta is called the coefficient of volume expansion, and you can find this in a table as well since it's specific to the substance. And the relationship between beta and alpha is that beta equals 3 alpha. Example 7, a hollow aluminum cylinder 20 centimeters deep has an internal capacity of 2 liters at 20 degrees Celsius. It is completely filled with turpentine at 20 degrees. The turpentine and the aluminum are warmed together to 80 degrees Celsius. A, how much turpentine overflows? And B, what is the volume of the turpentine remaining at 80 degrees Celsius? Okay, so we have alpha for aluminum, and we can multiply by that by 3 to find beta. And then beta for turpentine is 9 times 10 to the negative 4 per degree Celsius. So we can see already that, of course, the turpentine would overflow because beta is greater than, this will be even times 3. It will be less than beta for turpentine. Okay, so if we were to write an equation for both, delta V for the aluminum is Vi times 3 alpha aluminum delta T, and then delta V for the turpentine would be Vi beta for the turpentine, also delta T, since both expand and they undergo the same temperature change. So then delta V overall, to figure out the total change in the turpentine, or how much will overflow, we'll have delta V for the turpentine minus delta V for the aluminum cylinder. So this is going to be Vi delta T beta turpentine minus beta for the aluminum. So our initial volume is 2 liters. And there's an increase from 20 degrees to 80 degrees, so 60 degrees. And then we'll have 9 times 10 to the negative 4 minus 3 times 24 times 10 to the negative 6, which is 0.09936 liters. So that's how much of this liquid will overflow. Then part B is asking us what is the final volume at 80 degrees, and what we know is that it will completely fill this cylinder. So it will have the same volume of the cylinder at that time. So we'll have final volume is VF equals VI 1 plus 3 alpha delta T for the aluminum. So that's 2 liters, 1 plus 3 times 24 times 10 to the negative 6 per degree Celsius times the increase of 60 degrees, which gives 2.00864 liters. And it can be helpful to keep extra sig figs for these volume expansion questions, since we're not always seeing a large change in volume, but it is something that is still significant. Suppose you have 2 kilograms of water whose density at 4 degrees is 1,000 kilograms per meter cubed. A, what volume does the water occupy at this temperature? B, the coefficient of volume expansion for water is 210 times 10 to the negative 6 per degree Celsius. If the water is heated to 20 degrees Celsius, what volume will the water occupy, and what is its density? So this density that we usually assume for water is actually at 4 degrees, so that's what we're going to investigate in this example. The mass is constant, that won't change dependent on the temperature. So density is mass over volume. We can rearrange this to find the volume. It's the mass over the density. So we have 2 kilograms over this density, 1,000 kilograms per meter cubed, which equals 2 times 10 to the negative 3 meters cubed for the initial volume at 4 degrees. All right, now to find the final volume so we can find the final temperature, we have VF equals VI 1 plus beta delta T. So that's 2 times 10 to the negative 3 meters cubed, 1 plus 210 times 10 to the negative 6 degrees Celsius inverse times 16 degrees Celsius, since it's being increased to 20 degrees from 4 degrees. Let's keep extra sig figs here since it will be a small change. It's a good idea to do that with all expansion problems. So 2.00672 times 10 to the negative 3 meters cubed. Okay, and let's see how this changes the density at 20 degrees. The density is mass over volume, 2 kilograms over 2.00672 times 10 to the negative 3 meters cubed, which gives 996.7 kilograms per meter cubed. So we can see that there is a slight change at 20 degrees from the density of water compared to the standard value that we use at 4 degrees. However, this shows change in 3 sig figs. If we were to round to even 2 sig figs, we would still have 1,000 kilograms per meter cubed. So it is a good estimate to use that value.